In this lesson, you will learn to identify series and to use sigma notation. Now, there is a difference between series and sequence. Whereas most people assume them to be the same, and those terms are used interchangeably, there is a slight nuance between those two terms. So they're very similar, but there is a little difference. A sequence is simply a list of numbers with a particular pattern. A series, on the other hand, is when those terms of the sequence are added together. So for example, we have a finite sequence given as being 3, 7, 11, 15, and 19. A finite series would be adding those numbers together. So 3 plus 7 plus 11 plus 15 plus 19. An example of an infinite sequence would be 1/2, 1/4, 1/8, 1/16, etc., where we have the 3 dots at the end to signify that it's infinite. An infinite series would be adding those together. So 1/2 plus 1/4 plus 1/8 plus 1/16, and etc. An arithmetic sequence would be something like this, where you're adding 4 every time to get to the next number. So 3 plus 4 is 7, 7 plus 4 is 11, and etc. Whereas an arithmetic series would be adding those together. 3 plus 7 plus 11, etc. And then a geometric sequence would be something where you're multiplying to get to the next term. So here we're multiplying by 1/2 to get to each term. So 8 times 1/2 is 4, 4 times 1/2 is 2, and etc. A geometric series is when you add those together to give me 8 plus 4 plus 2, and etc. Now when we deal with series, where we add everything together, there is a quick way that we can show or represent a series. And that is by using what is called a summation sign. It's a way to express a series in a shortened manner. The symbol is right here, which is a Greek capital sigma. And in Greek, a sigma is the letter S in English, and this is a capital sigma. So this is also called summation notation or sigma notation because it's a sigma. Now how this works is here we see a sigma with n equals 3 on the bottom, a 45 on the top, and then 2n on the side. What this means is that we are going to look at the 2n, and in place of n, we're going to plug in every number starting from 3 all the way to 45. So I'd have 2 times 3 would be the first term, and then I plug a 4 in for n to get 2 times 4, then plug a 5 in for n to get 2 times 5, plug a 6 in, and etc. Keep going until you reach 2 times 45. And you stop at 45 because that is the number on the top of the sigma notation. Now here's another example where we have a 1 in the bottom, 4 on the top, and then 12 over n in parentheses. So once again, we're going to plug in every number from 1 all the way to 4 in place of n. So instead of 12 over n, we would have 12 over 1. Then we plug a 2 in to get 12 over 2, and then plug a 3 and then a 4 in to get this series. Now, when we write it out in this format as a series, where everything is being added together, that is called expanded form. So right here in red would be your expanded form, and then over on the left side would be your summation notation. So going from summation notation to expanded form really isn't too bad. We're just plugging in numbers. But going the other way, from expanded form back into sigma notation, can be kind of complicated and a little more difficult to perform. So here's the most basic example where you can convert back to summation notation. And so what we want to do when we try to do this is we know that we need the summation sign, something on the bottom, something on the top, and then something on the right side. And your first step that you want to do whenever you try to find the summation notation is pair up each number with the term number. So here we see 2 would be term 1, 4 is term 2, 6 is term 3, and etc. So we know we're going to be starting with a term number of 1, but the question is, how far are we going to go to get to 100? How many terms do we have to get to 100? So what we do is we look at the pattern, not horizontally, not to get from 2 to 4 to 6, etc., but we're going to look at the pattern vertically. What is the pattern to get from 1 to 2, then from 2 to 4, then 3 to 6, etc.? Well, we notice the pattern vertically is you're multiplying the term number times 2. So keeping that pattern going, this term number over here times 2 would give me 100. So what times 2 is 100? That's going to be 50. So when I set up my summation notation, I'm starting with term number 1, and I'm going all the way to 50. So the number down here is 1, the number on the top is going to be 50. And the question is, what is going to go on the right side? Well, on the right side is going to be your pattern vertically. So the pattern we said was we take 2 times the term number, which we can use the letter n to be the term number. So our pattern is 2 times n, and that's going to be what goes on the right. And we can double check our answer by plugging back in the numbers 1 through 50 in place of n. 2 times 1 would give me 2, then plug a 2 in to get 2 times 2, which gives me the 4, 2 times 3 gives me 6, and etc. So if we plug the numbers back in, we would get the same series that we started with. Now this next example, we need to do the same kind of process, but this one is a little more difficult. So we still pair up the term number with each of the numbers. That should be your step 1. And then we need to figure out how many terms do we have to get to 85. Well, if we look at the pattern vertically, so look at the pattern from 1 to 5, from 2 to 9, 3 to 13, and 4 to 17. If we keep that pattern going, we can find this term number. Well, the pattern here is not as obvious, right? We can't just multiply 1 by something to get to 5, and then 2 by the same number to get to 9, right? Because 1 times 5 is 5, but 2 times 5 would give me 10, so that doesn't work. So to find the pattern vertically, what I can do is look for a moment at the pattern horizontally. So the pattern horizontally is we're adding 4 every time, right? We add 4 to get to 9. 9 plus 4 is 13. And we're going to use that 4 as part of the pattern vertically. So a technique we can use is take the 4, multiply it by n, the term number, and then add or subtract as needed. So if we take 4 times n, what do we need to add or subtract? Well, n is the term number. So looking at this first set of numbers, the 1 and the 5, 4 times 1 gives me 4, but what do I need to add to that to give me the 5? Well, add 1 to 4 to get 5. So the pattern vertically, if I take 4 times 1 plus 1, I get 5. 4 times 2 plus 1 gives me 9. 4 times 3 plus 1 is 13, and etc. So the pattern vertically is 4n plus 1. So keeping that pattern going, this number right here, this term number, if I take 4n plus 1, that's going to equal 85. So I can solve this for n, subtract 1 to get 4n equals 84, divide both sides by 4, we get n equals 21. So my term number here is going to be 21. So when I set up my summation notation, I know that we need something on the bottom, the top, and on the right. Well, the bottom and the top would be what term numbers are we going to be plugging in. And so we start with a 1 and then go all the way to 21. So I plug a 1 in on the bottom, 21 on the top, and then on the right side is my pattern vertically. Well, the pattern we already found to be 4n plus 1. So that's what's going to go on the right side. And we're done. We found how to write this in summation notation. We can double check our answer by plugging back in the numbers 1 through 21, back in for n, to see if we get back out the series that we started with. And in this case we would. Plug a 1 in, we get 4 plus 1, which gives me 5. Plug a 2 in, we get 4 times 2 plus 1, which gives me 9. And it's going to work for the rest of them as well. Here's another example where it's not an arithmetic sequence. or series I should say, because we're not adding the same thing to get to the next term every time. There is a pattern, but the pattern is not an arithmetic sequence. So the question is, how do we write this using summation notation? Well, what I can do, once again, is set up each number with the term number. So the 1 would be term 1, 1/4 is term 2, 1/9 is term 3, 1/16 is term 4, and etc. And it keeps going forever because it's an infinite series. And so a symbol we can use for infinity is a sideways 8. This is your symbol for infinity. So when I set up my summation notation, I need something in the bottom, on the top, and on the right hand side. And now the question is, what are we going to put in each of these locations? Well, the bottom and the top are going to be the term numbers that we're dealing with. So here we're starting at term 1, so put a 1 in the bottom, and then you're going to put an infinity on the top because we're going to keep going forever and ever. And now the question is, what do we put on the side? What we put on the side is the pattern vertically. How do we get from 1 to 1, or from 2 to 1/4, or 3 to 1/9, etc.? So maybe not as much the pattern, but what is the relationship between the term number and the number itself? Well, if we notice that 1, we can think of this as 1/1. Well, the numerator is always going to be 1. The numerator does not change. So the number on the right-hand side that I'm going to put in my summation notation would have a numerator of 1. And then the denominator is the only thing that is changing. So what is the relationship between the denominator? Well, if we see the 1 and the 1, 2 and 4, 3 and 9, 4 and 16, notice the pattern is that we take the term number and then square it. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So the pattern, or the relationship between the term number and the denominator, is that we take the term number and then square it. So we represent that by n squared. So my summation notation would be n equals 1 to infinity of 1 over n squared. And that's it. Now in this example, we are dealing with a geometric series, which means to get from term to term, you're multiplying by some number. So here we get from -9 to 3 by multiplying by a negative, and then it's going to be 1/3. So multiply by -1/3 to get to 3. -1/3 times 3 would give you a -1, and etc. So we want to pair up each number with a term number. So -9 is term 1, 3 is term 2, etc. And this is infinite, so it's going to keep going forever. And your symbol for infinity is the sideways 8. And now in writing your summation notation, we know we need something on the bottom, the top, and on the side. Now for the geometric series especially, we can write this in many different ways, and yet it's helpful many times to begin by having n equals 1 at the bottom. So here we see that we're starting at term 1, and then we're going to infinity. That's going to be on the top. But there's times, and we'll show another way to write this after this example, but we can write this without starting at n equals 1, but could start at some other number. Could start at 0, could start at 2, 3, 4, etc. So to do this, we are going to start with 1 and then go to infinity. And the question is, what is going to go on the right-hand side? Well, for the geometric especially, we're more concerned with the pattern horizontally. So to get from term to term, we're multiplying by -1/3. So that's going to be part of the pattern that we need to put on this right side. And to get from term to term, we keep multiplying by -1/3. So we keep doing this forever, and so we're going to put an n up here, meaning we can keep multiplying n number of times to get from term to term. But the question is, how do we start it out? Well, we need a -9 to begin. So -1/3 to the n power, what do we need to put here in the front to compensate, to get the -9 back out at the beginning? Well, if we start with a 1, kind of thinking now the other way, if we plug a 1 in for n, we're going to have negative 1/3 to the first power, or just negative 1/3. But I need to get negative 9 back out. So what do I have to multiply by negative 1/3 to get to negative 9? Well, if I take 27, and then 1/3 of 27 would give me 9, and positive 27 times a negative would give you a negative 9. So if I put a 27 in front, right here, for that first term, I'm going to get a negative 9. And then if I put a 2 in for n, I now have 27 times negative 1/3 squared, which would give you 27 times a positive 1 over 9, which would be a positive 3, which is the next term. So this appears to be working because every time now we're going to multiply by negative 1/3 to get to the next number. So if we put a 3 in for n, we have negative 1/3 to the third power, which would be the same series, except now we're going to multiply by negative 1/3 again to get to the next term. So this would be your pattern, and that would be your solution. Put a 1 in for the bottom, infinity on the top, and then 27 times negative 1/3 to the n power over here. Now, like I said, there are other ways that we can write this. And I'm going to show you one other way that you could represent the same summation notation. Instead of starting out the terms as 1, term 2, term 3, term 4, we could begin by starting out having negative 9 be term 0, 3 be term 1, negative 1 be term 2, and etc. And the pattern is still the same. I'm multiplying by negative 1/3 times a negative 1/3. And when I write this, now I'm going to start at n equals 0 going to infinity. And I still have the negative 1/3 as part of the pattern. And I'm still going to be repeatedly multiplying by negative 1/3. So I'm going to put an n up here as well. But the difference now is going to be the number in the front. Where before I needed a 27, but here, if I start at 0, I plug a 0 in for n, I now have negative 1/3 to the 0 power, which is going to be 1. But I need to get a 9 out, or negative 9 out for the first term. So what do I multiply 1 by to get to negative 9? We'll multiply by negative 9, of course. So my solution, the way I can write this, would be n equals 0 to infinity of negative 9 times negative 1/3 to the n power. And I'll show you one more way you can write this even. You could start at, let's go to n equals 1 again, to infinity, and then you have the same pattern, negative 1/3. And then instead, if we want to start at negative 9, put a negative 9 here, I could put n minus 1 for my exponent. Where now if I plug in everything, plug a 1 in for n, I would now have negative 9 times negative 1/3 to the 1 minus 1 or 0 power, which would begin by giving me a negative 9, because negative 1/3 to the 0 power is 1. And then the next term, plug a 2 in, you have negative 9 times negative 1/3 to the 2 minus 1 or first power, which would give you a positive 3. And you could keep going, and we find that the series would still be the same. And that's just 3 different ways you can write it. There are, I'd almost say, an infinite number of ways that you could write the summation notation. And that concludes our lesson for today. We will see you next time.